Okay, we're now going to start talking about the regular polygons, and we're going to talk about how we can find the area of the regular polygons. We look at a pentagon here as an example, okay? Regular, of course, meaning all sides are equal, all angles are equal. We knew how to find the central angle is 360 divided by the number of sides. So for the pentagon, that was 72, okay? We then defined the parts of it. We saw that the segments PD, PE, PA were radii of the circumscribed circle, and they are called the radii of the polygon. All right, and so all those segments, as we showed there, are labeled the radii of the polygon. We saw we could inscribe the circle within here, okay, and that the segment there, PR, is the radius of the inscribed circle, but that's also the radius of the polygon. I'm sorry, the apothem or apothem of the polygon, the apothem of the polygon, okay? And so we actually were at a stalemate right then because we couldn't find the area of that because this triangle inside here did not collapse to one of those familiar ones. We're going to come back and look at that now using trigonometry. So let's run through and refresh your memory on all these polygons. Remember the hexagon central angle 360 divided by 660, okay? So then each one of these was an equilateral triangle. And we reasoned out that if we found the area of that one triangle, okay, and multiplied it by the area of, by 6, that would give us the area of the regular hexagon there, okay? Of course, to find the area of that, we broke it down and we remembered the formula, the half the height times the base. So, and of course that height there was separating the figure into two 30, 60, 90s. That height is also called, that the height PT is also called the apothem of the polygon. So if you remember, we went through, we looked at that. We found that apothem using the 30, 60, 90 triangle principle, okay? And we're able to find that apothem, that length PT, was 4√3. So that allowed us to find the area of one of the triangles using the half the height times the base formula, and that gave us that triangle shown there in yellow is area 16√3. If we multiply that by 6, since there are 6 triangles, we get the area of the polygon. Okay. If we looked at that from another way, we saw that if we broke these up into the 6 triangles, we could find the area of the 6 triangles. Okay, and we justified that the height of each one of those triangles, as marked there, PS, PT, PU, were all the apothems, the apothems of the polygon. Okay, so they all have the same value. So if we looked at the area of each of the figures separately as triangles, and then did a little algebra, took out the common factor, which was 1/2 A, 1/2 the apothem. We saw that the sum of these segments, A, B, B, C, C, D, and so on, were the perimeter. So therefore, we had a formula that worked for us for regular polygons: half the apothem times the perimeter, half the apothem times the perimeter. And since all sides were 6, and there were all sides were 6, and there were 8 of them, okay, then the area is the perimeter is 98, and the apothem is 4√3, so the area is 96√3. So, okay, so equilateral triangle, we were able to reason that out too, because that divided into a central angle of 120, which when we split that down was another 30, 60, 90. Okay, so we were able to work with that before. You can go back, review that slideshow that we offered you earlier, but okay, the same familiar formula: 1/2 the apothem times the perimeter, and of course the apothem was found using the principles behind the 30, 60, 90 for the square. The apothem was also found using the principles of the 45, 45, 90, but we're left with a problem when we had some other kind of regular polygon. So we're going to use trigonometry as illustrated here with this presentation to show you that. So here we are. We're back with this pentagon. Okay, so we're after the area of this pentagon. All we know about it is the sides are 6. So the formula is half the apothem times the perimeter, and of course the perimeter would be 30, but we don't know what the apothem is, that segment PR. But okay, so there's our formula, and there's the information as I just stated. Okay, so the apothem is the value in question. We have to find that, and we're going to use trigonometry to find that because we know angle measurements and we know how we can find that apothem, as we're going to outline for you here. Okay, so since it is a regular polygon, since the central angle 360 divided by n makes that central angle 72 degrees. That is any of these angles at P. CPB 72, okay, DPC is 72, BPA is 72. But when we draw that apothem, we can see that we break that up into, we bisect that angle 72 up here. So the angle here between the blue and the green segment is 36. We know that, okay? We didn't have to measure that, we know that. So we know that angle is 36, okay? And we know that this side BR is half the length of one side, which is 3. So we're going to use the trigonometry, the tangent ratio, okay? So we're saying that the tangent of angle BPR, the tangent of angle BPR is BR, say is the segment length BR over RP. RP is the apothem, okay? So so here we go. We're putting those values in. We know that BR is half of the total side, so it is, its length is 3. We said that the tangent of the angle is 36. Okay, so we get a decimal value of the tangent of 36 is 0.73. We go back to this equation, we put in our unknown values. Okay, so the tangent is 0.73 is equal to 3 over x, cross multiplying, we get 0.73, x equals 3. Dividing, we find the value of x, the value of the apothem, 4.1. And with the value of the apothem, of course, we can now come and we can find the area of the polygon. So having the apothem as 4.1, go back, look at this right triangle, use the tangent ratio. Tangent of 36 is 3 over x. Solving for x, 4.1. Okay, putting it into our area formula for the polygon, we get the area 61.5. Okay, look at another one. Now we look at the octagon. We have the octagon here. The apothem is 10 inches. Okay, the apothem here is 10 inches. That means the segment DF is 10. The segment DF is 10. We do not know the sides. Okay. But we do know the central angle. The central angle here, of course, is 45 degrees. 360 divided by 8, the number of sides, okay? We need to recall the area formula for the apothem. 1/2 the apothem times the perimeter, okay? We have the apothem. We do not have the perimeter. We need to find the perimeter. We can find the perimeter using trigonometry. We look at our triangle up here. Our triangle here. The 45-degree angle is the angle EDG. If we draw the apothem in right here, the angle here at EDF, the angle at EDF is half that 45, 22.5. 22.5. We have the apothem over here is 10. Trigonometry will be able to find the segment EF. With the segment EF, we can find EG. With EG, we can find the perimeter, okay? All right, so that's what we've reasoned right here. Okay, we look at the triangle EDF. All right, we recognize again the tangent of the angle EDF. The tangent of 22.5 is equal to EF over the apothem of 10. So tangent of 22.5 is EF over DF. Okay, tangent of 25, our calculator says that is, okay, 0.414 is equal to the unknown value EF over 10. Cross multiply, we found that x is 4.4. X is standing in as the value EF, 4.14. Twice that would be the length of EG. EG, therefore, would be 8.28. Okay, The perimeter would therefore be 8 of those sides, which would be 66.24, going to the perimeter, going to the area formula for regular polygons. Half the apothem times the perimeter. Here it is, 1/2 10 times 66.24. 331.2 is the area of this regular polygon. Again, look at this. Look at the angle. Look at the triangle form with the central angle, which is right here, EDG. Central angle is 45, 360 divided by 8, okay? Drawing the apothem right here, and use the trigonometry to find, okay, the length EF. The tangent of this angle, 22.5, is EF over the apothem value of 10, okay? We recently saw in class the new formula for the area of a triangle. Once you have the angle value, okay, and 2 sides, okay, we have the new formula that says it's 1/2 the product of the 2 sides and the angle, the sine of the angle in between it. That's what we're showing you here. The thing I wanted to focus on mostly, though, however, is how we use the trigonometry, to determine the area for regular polygons, okay? Regular polygons, specifically those regular polygons like octagons and pentagons, okay, dodecagons, decagons, those kind of polygons which we were not able to find the apothem value before. We are now able to find that value using principles of trigonometry, okay? So there you have it.